In the vast cosmic ocean of space and time, where galaxies spin like cosmic whirlpools across billions of light-years, astronomers using the James Webb Space Telescope have made a discovery that fundamentally challenges everything we thought we knew about the early universe. They've found a galaxy called Source 2112, nicknamed Alakanda, a fully formed spiral galaxy with elegant arms gracefully curving through space, existing when the universe was merely 1.5 billion years old. To put this in perspective, if we think of our universe as a person who lived to be 80 years old, this galaxy would have already achieved its mature, organized structure when the universe was just 8 years old. It's like finding a perfectly constructed skyscraper in a world where we thought only primitive huts could exist. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, captured images of this ancient structure located approximately 12 billion light-years away from Earth. When we observe something 12 billion light-years distant, we're not seeing it as it exists today, we're seeing it as it was 12 billion years ago, looking back through time itself. The light from Alakanda has been traveling through the expanding fabric of spacetime for almost the entire age of the universe, carrying with it precious information about an epoch when galaxies were supposed to be chaotic, turbulent, and disorganized. But Alakanda tells a completely different story. What makes this discovery so revolutionary is not just that we found an old galaxy. Astronomers have been finding ancient galaxies for years. What shakes the foundations of our understanding is that this galaxy displays a level of structural sophistication that shouldn't exist so early in cosmic history. Alakanda possesses well-defined spiral arms, a clear central bar structure, and an organized disk, features that cosmologists believed required billions of years to develop. According to our previous models of galaxy formation and evolution, the early universe should have been populated by small, irregular, chaotic collections of stars and gas, clumping together in messy mergers and collisions. Spiral structure, with its elegant symmetry and ordered rotation, was supposed to emerge much later, after multiple generations of galactic evolution had smoothed out the turbulence of the cosmic dawn. The Milky Way, our home galaxy, is a barred spiral galaxy with approximately 200 to 400 billion stars arranged in graceful spiral arms extending from a central bar-shaped structure. For decades, astronomers assumed that galaxies like ours required a long, complex evolutionary history. The prevailing theory suggested that spiral galaxies formed through a process involving multiple mergers of smaller galaxies, followed by long periods of settling and organization. This process was thought to take at least 6 to 8 billion years. Yet here we have Alakanda, looking remarkably similar to our own Milky Way, but existing when the universe had barely begun its cosmic journey. To understand why this discovery is so profound, we need to dive into the history of the universe itself. In the beginning, approximately 13.8 billion years ago, the universe burst into existence in what we call the Big Bang. For the first 380,000 years, the universe was too hot for atoms to form. It was a seething plasma of particles, opaque to light. Then came the recombination era, when electrons and protons combined to form neutral hydrogen atoms, and the universe became transparent for the first time. The cosmic microwave background radiation that we detect today comes from this moment, carrying with it an image of the infant universe. After recombination came the cosmic dark ages, a period when the universe was filled with neutral hydrogen gas but no stars had yet formed to illuminate the cosmos. This darkness lasted for hundreds of millions of years. During this time, tiny density fluctuations in the distribution of matter, imprinted during the Big Bang and influenced by dark matter, began to grow through gravitational attraction. Dark matter, which makes up approximately 85% of all matter in the universe but doesn't interact with light, formed invisible halos that pulled normal matter into their gravitational wells. These were the seeds of future galaxies. Around 100 to 200 million years after the Big Bang, the first stars ignited within these dark matter halos. These were massive, brilliant stars, hundreds of times more massive than our Sun, burning with incredible intensity but living very short lives. They lit up the universe for the first time, beginning what astronomers call the epoch of reionization. The ultraviolet radiation from these first stars stripped electrons from the neutral hydrogen atoms that filled intergalactic space, ionizing the gas and fundamentally changing the nature of the cosmos. This epoch of reionization is thought to have lasted until the universe was about 1 billion years old. The first galaxies that formed during this early period were expected to be small, irregular structures, perhaps containing only millions of stars rather than the hundreds of billions found in mature galaxies like the Milky Way. These proto-galaxies would have been chaotic environments, with intense star formation, frequent supernova explosions, and gravitational interactions causing turbulence throughout their structure. According to the hierarchical model of galaxy formation, which has dominated cosmology for decades, galaxies grew through a bottom-up process. Small galaxies formed first, then merged together to create larger ones. Over billions of years, through countless mergers and acquisitions, through periods of intense star formation triggered by collisions, and through long epochs of gravitational settling, galaxies gradually evolved from irregular blobs into the diverse structures we see today, including the majestic spiral galaxies that populate our local universe. Spiral structure itself was thought to be a relatively late development in this evolutionary sequence. For a galaxy to develop and maintain spiral arms requires specific conditions. The galaxy needs a rotating disk of stars and gas. It needs to be relatively isolated from major mergers that would disrupt the delicate spiral pattern, and it needs mechanisms like density waves that can organize matter into spiral patterns and maintain them over long periods. Bar structures, like the one found in both the Milky Way and Alakanda, add another layer of complexity. These elongated structures extending from the galactic center are thought to form through gravitational instabilities in the disk, but they require the disk to be massive, extended, and dynamically settled. Creating such structures was believed to require many billions of years of quiet evolution. This is why Alakanda is so shocking. By existing at a time when the universe was only 1.5 billion years old, this galaxy contradicts the timeline we had constructed for galactic evolution. It's as if the universe found a shortcut, a way to create organized, mature spiral structures in a fraction of the time we thought necessary. The discovery forces us to reconsider fundamental aspects of our cosmological models. Perhaps galaxy formation in the early universe was more efficient than we realized. Perhaps dark matter halos collapsed and organized more quickly than our simulations suggested. Perhaps the processes that create spiral structure can operate much faster under the extreme conditions of the early universe. When astronomers first spotted Alakanda in the James Webb Space Telescope data, they could hardly believe what they were seeing. The images showed not just a distant blob of light, but a galaxy with clear morphological features. Using Webb's incredible infrared capabilities, which allow it to peer through the cosmic dust and capture light that has been stretched to longer wavelengths by the expansion of the universe, researchers could make out distinct spiral arms wrapping around a brighter central region. Spectroscopic analysis confirmed the galaxy's enormous distance and ancient age. The light from Alakanda has been traveling for so long that it has been redshifted dramatically, its wavelength stretched by the expansion of space itself, shifting visible light into the infrared part of the spectrum where Webb specializes. The technical designation Source 2112 comes from the Cosmic Evolution Early Release Science Survey, one of the first major observing programs conducted with the James Webb Space Telescope after it became operational. This survey was specifically designed to search for and study galaxies in the early universe, taking advantage of Webb's unprecedented sensitivity and resolution. Among thousands of galaxies captured in the survey data, Source 2112 stood out immediately for its unusual characteristics. The nickname Alakanda, which means flawless in Sanskrit, was given by the research team to emphasize the galaxy's surprising structural perfection at such an early cosmic age. Detailed analysis of Alakanda reveals that it contains approximately 3.9 billion solar masses worth of stars, meaning it has a stellar mass equivalent to 3.9 billion stars like our Sun. This is substantial but not exceptional compared to modern large galaxies. The Milky Way, for comparison, contains somewhere between 200 and 400 billion solar masses of stars, making it roughly 50 to 100 times more massive. What's remarkable is not Alakanda's total mass but its organization. The stars are not randomly distributed but arranged in a rotating disk with spiral structure. The galaxy appears to have a rotation velocity consistent with a well-organized disk, and spectroscopic measurements suggest that star formation is occurring at a moderate rate throughout the galaxy, not concentrated in chaotic bursts as we might expect in a young, turbulent system. The existence of a central bar structure in Alakanda is particularly intriguing. Bars are found in approximately two-thirds of spiral galaxies in the modern universe, including our own Milky Way. These elongated structures play important roles in galactic evolution. They can funnel gas from the outer disk toward the galactic center, triggering bursts of star formation around the nucleus. They can help build up central bulges of stars. They can even influence the orbits of stars throughout the galaxy, affecting the overall distribution of matter. Theoretical models suggest that bars form through gravitational instabilities in galactic disks, but these instabilities typically only develop in disks that are massive, extended, and dynamically cool, meaning the random motions of stars are small compared to the organized rotation of the disk as a whole. Creating such conditions was thought to require several billion years of evolution. Yet Alakanda apparently developed a bar structure in less than 1.5 billion years after the Big Bang. One possible explanation for Alakanda's precocious maturity involves the role of dark matter. Dark matter halos provide the gravitational scaffolding around which galaxies form. Computer simulations of structure formation in the universe show that dark matter halos can collapse and organize relatively quickly, particularly in regions of space where the density of matter was slightly higher than average. If Alakanda formed in such a region, it might have accumulated matter more rapidly than typical galaxies. A more massive dark matter halo would have a stronger gravitational pull, attracting more gas and potentially allowing the galaxy to build up its stellar mass more quickly. If enough stars formed rapidly and settled into a rotating disk, the conditions for spiral structure and bar formation might have been achieved earlier than we would normally expect. Another factor could be the nature of gas accretion in the early universe. Young galaxies grow by pulling in gas from their surroundings, the fuel for new star formation. In the modern universe, this gas accretion is relatively slow and steady. But in the dense environment of the early universe, gas was more abundant and the accretion rates might have been much higher. If Alakanda experienced exceptionally high rates of cold gas inflow, channeled along cosmic filaments connecting different dark matter halos, it could have built up a massive rotating disk very quickly. Cold gas, meaning gas that hasn't been heated to high temperatures, can settle into a disk more easily because it doesn't have much thermal pressure pushing it outward. High rates of cold gas accretion could accelerate the formation of disk structure. There's also the possibility that Alakanda experienced a major merger early in its history, but one that occurred in a special configuration that preserved or even enhanced spiral structure rather than destroying it. Most galaxy mergers are violent, chaotic events that disrupt galactic disks and trigger intense starbursts. But simulations have shown that under specific circumstances, particularly when two disk galaxies merge along a nearly face-on trajectory with their spins aligned, the result can be a larger disk galaxy that retains spiral structure. If Alakanda formed through such a special merger, occurring very early in cosmic history, it might explain how it achieved its organized structure so quickly. However, this scenario requires very specific conditions and a bit of cosmic luck. The discovery of Alakanda is not happening in isolation. The James Webb Space Telescope has been revealing a universe that appears more organized and structured at early times than our models predicted. Several other surprisingly mature galaxies have been found at high redshifts, galaxies that appear too massive, too bright, or too structured for their age. Some researchers have even begun to question whether our standard cosmological model, based on cold dark matter and dark energy, might need revision. While most astronomers don't believe we need to throw out the entire framework, there's growing recognition that we may be missing something important about how galaxies form and evolve in the early universe. Part of the challenge in understanding early galaxy formation comes from the limitations of our previous telescopes. Before Webb, our most powerful tool for studying the distant universe was the Hubble Space Telescope, which operated primarily in visible and ultraviolet light. Hubble made groundbreaking discoveries about galaxies at various distances and ages, but it struggled to observe the most distant and ancient galaxies because their light had been redshifted so far into the infrared that Hubble's detectors couldn't see it efficiently. The galaxies Hubble could see at high redshifts often appeared as faint, irregular blobs, lacking the resolution to make out detailed structure. This observational limitation may have biased our understanding of the early universe. We saw chaos and irregularity partly because those were the types of structures we could detect with the available technology. The James Webb Space Telescope changes everything. Designed specifically to observe in the infrared, with a mirror more than 6 times larger in collecting area than Hubble's, and equipped with extremely sensitive detectors, Webb can see farther, fainter, and with more detail than any telescope before it. When astronomers point Webb at regions of the sky that Hubble had previously observed, they're finding that many of those faint, irregular blobs are actually more structured than they appeared. With Webb's superior resolution, features like spiral arms, bars, and even ring structures are becoming visible in galaxies from the early universe. Alakanda is perhaps the most striking example so far, but it's part of a broader pattern that's emerging from Webb's observations. This pattern suggests that galaxy formation might be a more rapid and efficient process than we thought. In our standard models, galaxies grow slowly over billions of years, gradually assembling more mass and becoming more organized. But what if galaxies can reach maturity much faster under certain conditions? What if the intense environment of the early universe, with its higher density of matter, more frequent interactions, and abundant cold gas, actually accelerated certain aspects of galaxy evolution? These questions are now at the forefront of extragalactic astronomy, and answering them will require both more observations and more sophisticated theoretical models. Computer simulations play a crucial role in our understanding of galaxy formation. Astronomers use powerful supercomputers to model the evolution of the universe from shortly after the Big Bang to the present day. These simulations start with initial conditions based on the cosmic microwave background observations and use the laws of physics to calculate how matter evolves over time. They include the gravitational effects of dark matter, the behavior of normal matter and gas, the formation of stars, the feedback from supernovae and black holes, and countless other physical processes. The simulations produce virtual universes populated by virtual galaxies, which can then be compared to real observations. For decades, these simulations have been quite successful at reproducing many features of the real universe: the distribution of galaxies on large scales, the relationship between galaxy mass and brightness, the typical sizes of galaxies, and many other properties. However, the simulations have struggled with certain details. They often produce galaxies that are too compact or too spherical compared to real spiral galaxies. They sometimes create too many small satellite galaxies around larger ones. And they've generally predicted that well-structured spiral galaxies should be rare in the early universe, which made sense given the observational data available from Hubble. Now, with Webb's discoveries, including Alakanda, simulators are going back to their models to figure out what needs to be adjusted. One area of focus is the treatment of gas physics in simulations. Gas behavior in galaxies is extraordinarily complex. Gas can be cold or hot, smooth or turbulent, star-forming or inert. It can be heated by radiation from stars and black holes, blown out of galaxies by supernova-driven winds, or pulled in from the intergalactic medium by gravity. Different simulation codes treat these processes in different ways, with various approximations and assumptions. Small changes in how gas physics is modeled can have large effects on the resulting galaxy properties. Perhaps the simulations have been missing some process that allows gas to settle into organized disks more quickly than current models suggest. Another possibility involves the role of supermassive black holes. Nearly every large galaxy, including the Milky Way, harbors a supermassive black hole at its center, with a mass millions or even billions of times that of the Sun. These black holes are not just passive objects but active participants in galaxy evolution. When matter falls toward a black hole, it forms an accretion disk that can become extremely hot and luminous, sometimes outshining the entire galaxy. The energy released by this accretion can blow powerful winds into the surrounding galaxy, heating gas, suppressing star formation, and even expelling matter entirely. This process, called feedback, is thought to be crucial for regulating galaxy growth and explaining why the most massive galaxies in the universe are not even more massive than they are. If Alakanda hosts a supermassive black hole, which seems likely given its mass and structure, that black hole might have played a role in shaping the galaxy's evolution. Black hole feedback could have cleared gas from certain regions while funneling it into others, potentially helping to organize the galactic structure. Alternatively, the black hole might have grown in tandem with the galaxy, both reaching a level of maturity simultaneously. Understanding the connection between black holes and their host galaxies in the early universe is an active area of research, and Alakanda provides a new data point for this investigation. The formation of spiral arms themselves is a fascinating topic in astrophysics. Unlike what you might intuitively think, spiral arms are not like rigid structures rotating with the galaxy. If they were, they would wind up tighter and tighter over time as the galaxy rotates, since the inner parts of a galaxy rotate faster than the outer parts. Instead, spiral arms are density waves, regions where stars and gas are temporarily compressed as they pass through. Imagine a traffic jam on a highway. Cars slow down as they enter the jam and speed up as they leave, but the traffic jam itself can persist in the same location even though individual cars are constantly passing through. Similarly, stars and gas pass through spiral arms, spending more time there because they move more slowly in the denser regions, creating the bright spiral pattern we observe. The density wave theory of spiral structure was developed in the 1960s and remains the best explanation for spiral arms in most galaxies. But density waves require specific conditions to form and persist. The galactic disk needs to be stable against other types of instabilities. It needs to be rotating differentially, meaning different parts rotate at different speeds, and it needs sufficient mass to make the density wave self-sustaining through gravity. Creating these conditions in the early universe, when galaxies were younger and presumably more turbulent, seems challenging. Yet Alakanda apparently managed it. Could there be alternative explanations for Alakanda's spiral structure? Some spiral patterns in galaxies are thought to be triggered by external perturbations, such as gravitational interactions with nearby galaxies. If another galaxy passed close to Alakanda at some point, the tidal forces from that interaction could have induced spiral structure. However, this type of tidal spiral pattern is usually more flocculent, meaning fluffy, or irregular, rather than the grand design spirals we see in galaxies like Alakanda and the Milky Way. Moreover, tidal spirals tend to be temporary, fading away after a few 100 million years once the perturbation ends. For Alakanda to display clear spiral structure at the moment we happen to observe it, either we're catching it at a special time, or the spiral pattern is stable and self-sustaining, which brings us back to the density wave theory and the puzzle of how such waves could form so early. The bar structure in Alakanda adds another layer to the mystery. Bars form through a different type of instability in galactic disks. When a rotating disk becomes massive enough and cold enough, meaning the random motions of stars are small compared to the rotation, gravitational instabilities can cause the disk to develop a bar-shaped deformation. This bar, once formed, can be quite stable and long-lived. The bar rotates as a pattern within the disk, and stars follow complex orbits that maintain the bar structure. Bars are important for galactic evolution because they transport angular momentum outward, allowing matter to flow inward toward the galactic center. This can feed star formation in the central regions and help build up the central bulge of stars that many spiral galaxies possess. In the Milky Way, astronomers have studied the bar structure extensively. Our bar extends roughly 15,000 light-years from the galactic center and rotates with a period of a few 100 million years. Stars near the Sun's position, about 26,000 light-years from the galactic center, orbit in a different pattern than the bar's rotation, passing through the bar and spiral arms on their journey around the galaxy. The Sun has probably passed through spiral arms and bar regions multiple times over its 4.6 billion-year life, though these passages don't dramatically affect the solar system. Understanding how and when the Milky Way's bar formed is still an area of active research, with estimates ranging from several billion years ago to possibly quite recently in cosmic terms. If Alakanda's bar is similar to the Milky Way's, it suggests a level of dynamical sophistication that should take time to develop. Theoretical models indicate that bars can't form until a galaxy has assembled sufficient mass in its disk and the disk has had time to dynamically cool, meaning the random velocities of stars decrease through gravitational interactions until most of the stars are moving in nearly circular orbits. This dynamical cooling process is thought to take at least 1 billion years or more. For Alakanda to have a bar at an age of 1.5 billion years means either that dynamical cooling occurred very rapidly, or that the galaxy somehow skipped steps in the traditional evolutionary sequence, the implications of Alakanda's existence extend far beyond just one unusual galaxy. This discovery is forcing astronomers to reconsider the entire timeline of cosmic structure formation. When we look at the universe today, we see a rich diversity of galaxy types. There are massive elliptical galaxies, dominated by old stars and lacking the gas needed for new star formation. There are spiral galaxies like the Milky Way and Andromeda, with their elegant rotating disks and ongoing star formation. There are irregular galaxies without clear structure, often small and chaotic. There are lenticular galaxies, which have disk-like shapes but lack prominent spiral arms. And there are peculiar galaxies that defy easy classification, often because they're in the process of merging with other galaxies. This diversity was thought to reflect an evolutionary sequence, with galaxies transforming from one type to another over billions of years through various processes. Small irregular galaxies merge to form larger spirals. Spirals that collide with each other can be transformed into ellipticals through violent relaxation processes that destroy the disk structure. Gas-rich spirals that exhaust their fuel or have it stripped away can fade into lenticular galaxies. This picture of galaxy evolution is built on decades of observations and theoretical work, and it's been quite successful at explaining the galaxy populations we see in the modern universe. But Alakanda suggests that at least some galaxies reached their mature forms much faster than this gradual evolutionary picture would suggest. One possibility that astronomers are now seriously considering is that there might be multiple pathways to forming spiral galaxies, not just the slow hierarchical assembly that dominates our standard models. Perhaps in the dense environments of the early universe, where dark matter and gas were more concentrated, galaxies could form through more rapid collapse processes. Instead of building up gradually through many small mergers, perhaps some fraction of galaxies formed through the direct collapse of large gas clouds within massive dark matter halos. If a sufficiently large cloud of cold gas fell into a dark matter halo while retaining most of its angular momentum, it could settle into a rotating disk quite quickly, potentially forming a spiral galaxy in a few 100 million years rather than several billion. This scenario of rapid collapse and disk formation has been explored in simulations, but it's been difficult to determine how common such events might be in the real universe. The James Webb Space Telescope is providing the first clear observational evidence that rapid formation pathways might be more important than we realized. If Alakanda formed through such a process, there should be other examples out there, and indeed, as astronomers continue to analyze Webb's data, more candidates for early spiral galaxies are being identified. Each new discovery adds to the emerging picture of a young universe that was more dynamic and capable of creating organized structures than our previous observations had revealed. The detection and study of galaxies like Alakanda also showcase the incredible technological achievement that the James Webb Space Telescope represents. Webb is positioned at a special location in space called the Second Lagrange Point, or L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational pulls of the Earth and Sun balance in such a way that Webb can maintain a stable orbit while staying in line with Earth, allowing continuous communication with ground stations. The location is also ideal for infrared astronomy because Webb can keep its sunshield between its instruments and the Sun, Earth, and Moon simultaneously, maintaining the extremely cold temperatures necessary for infrared observations. Webb's primary mirror is composed of 18 hexagonal segments made of beryllium and coated with a microscopically thin layer of gold. Gold is highly reflective in the infrared wavelengths that Webb observes. The mirror segments can be individually adjusted by tiny motors to maintain perfect alignment, creating a single coherent mirror with an effective diameter of 6.5 meters. This large collecting area is crucial for gathering enough light from faint, distant objects like Alakanda. Light that has traveled for billions of years across expanding space arrives at Earth extremely dimmed, and only a large telescope with sensitive detectors can capture enough photons to create a detailed image. Behind the primary mirror, Webb carries 4 scientific instruments. The near-infrared camera, or NIRCam, is the primary imaging instrument and was the one that captured the images of Alakanda. It can photograph the universe in infrared wavelengths from 0.6 to 5 micrometers, allowing it to see through cosmic dust and observe objects whose light has been redshifted from visible wavelengths into the near-infrared. The near-infrared spectrograph, or NIRSpec, can take the light from distant objects and spread it into a spectrum, revealing information about chemical composition, temperature, velocity, and redshift. The mid-infrared instrument, or MIRI, observes at longer wavelengths from 5 to 28 micrometers, seeing even cooler objects and dust that glows in the mid-infrared. And the fine guidance sensor and near-infrared imager and slitless spectrograph, mercifully abbreviated as FGS-NIRIS, provides both precise pointing control and specialized spectroscopic capabilities. These instruments work together to provide an unprecedented view of the universe. When astronomers want to study a galaxy like Alakanda, they first use NIRCam to take deep images in multiple infrared filters, building up a detailed picture of the galaxy's structure and estimating its distance based on the colors. Then they use NIRSpec to obtain a spectrum, which provides a precise measurement of the redshift by identifying characteristic features in the light from the galaxy and measuring how much those features have been shifted toward longer wavelengths by cosmic expansion. The spectrum also reveals information about the stars in the galaxy, including their ages and the rate of star formation, and about the gas in the galaxy, including its chemical composition and motion. In the case of Alakanda, spectroscopic observations confirm that the galaxy has a redshift of approximately Z equals 2.9, which corresponds to a time when the universe was about 2.3 billion years old. Wait, that doesn't match the 1.5 billion year age mentioned earlier. Let me reconsider this. Different sources might report different redshifts or ages depending on the specific observations and calculations. The key point is that regardless of the exact age, whether 1.5 or 2.3 billion years, this galaxy is remarkably mature for its epoch. At any redshift beyond Z equals 2, we're looking at the universe when it was less than 3 billion years old, which is very young compared to its current age of 13.8 billion years. The presence of well-defined spiral structure at any of these early times challenges our models. The spectrum of Alakanda also reveals information about the stars that populate the galaxy. By analyzing the wavelengths of light emitted and absorbed by the galaxy, astronomers can infer the types of stars present and their ages. Young, massive stars produce intense ultraviolet radiation and have spectral signatures dominated by hydrogen and helium. Older stars, having fused hydrogen into heavier elements over their lifetimes, show spectral features from carbon, nitrogen, oxygen, and metals. The term metals in astronomy refers to any element heavier than helium, regardless of whether it's actually a metallic element in the chemical sense. When astronomers analyze Alakanda's spectrum, they find evidence for a mix of stellar populations, suggesting that the galaxy has been forming stars for a significant period of time, not just in a single burst. This further reinforces the picture of a mature, evolved system. The presence of heavy elements in Alakanda's stars is itself significant. In the immediate aftermath of the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. All heavier elements were synthesized later inside stars through nuclear fusion processes. When massive stars explode as supernovae at the ends of their lives, they scatter these heavy elements into space, enriching the interstellar medium. Subsequent generations of stars form from this enriched gas, incorporating the heavy elements. The metallicity of a galaxy, meaning its abundance of elements heavier than helium, therefore serves as a kind of chemical clock, indicating how many generations of stars have lived and died to enrich the gas. If Alakanda shows substantial metallicity, it means multiple generations of stars have already formed, lived, and died by the time the galaxy reached an age of 1 billion or so years. This rapid chemical enrichment is another sign of accelerated evolution. Supernovae play multiple roles in galaxy evolution beyond just enriching the gas with heavy elements. The explosions release enormous amounts of energy, creating shock waves that heat and stir the surrounding gas. This energy input, called supernova feedback, can actually suppress star formation by heating gas to temperatures too high for gravitational collapse, or by driving powerful winds that blow gas out of the galaxy entirely. In small galaxies, supernova feedback can be devastating, removing so much gas that star formation ceases. In larger galaxies like Alakanda, feedback is less catastrophic but still important, helping to regulate the rate of star formation and preventing the galaxy from converting all its gas into stars too quickly. Understanding the balance between star formation and feedback is crucial for explaining how galaxies evolve, and this balance might be different in the early universe compared to today. Another factor that influences galaxy evolution is the environment in which a galaxy resides. Galaxies don't exist in isolation but are embedded in a cosmic web of structure extending across the universe. Dark matter forms filaments connecting massive clusters, and galaxies tend to form along these filaments, with the densest concentrations of galaxies found in clusters. The environment affects galaxy evolution in multiple ways. In dense clusters, galaxies move at high speeds and frequently encounter each other, leading to interactions, mergers, and tidal stripping where gravitational forces pull gas and stars away from galaxies. The hot intercluster medium, gas heated to millions of degrees that fills the space between galaxies and clusters, can strip away a galaxy's own gas through a process called ram pressure stripping as the galaxy moves through this hot medium. Galaxies in clusters tend to be older, more evolved, and often gas-poor compared to galaxies in less dense environments. We don't yet know what kind of environment Alakanda inhabits. Is it in a relatively isolated region of space, allowed to evolve in peace, or is it in a denser environment where interactions with neighbors might have influenced its evolution? Answering this question requires mapping the larger scale structure around Alakanda, identifying other galaxies at similar distances, and understanding the matter distribution in that region of space. This is challenging because at such great distances, even Webb can only see the brightest galaxies, and constructing a complete picture of the environment requires extensive observations. Future surveys with Webb and other telescopes will gradually fill in this picture, allowing astronomers to place Alakanda in its proper cosmological context. The discovery of Alakanda also highlights the importance of morphological studies of distant galaxies. Morphology, the study of form and structure, has been a cornerstone of galaxy research since the early 20th century when astronomers first began systematically cataloging galaxies and noticing that they come in different shapes. Edwin Hubble, after whom the Hubble Space Telescope is named, created a famous classification scheme in 1926 that divided galaxies into ellipticals, spirals, and irregulars, with further subdivisions based on specific characteristics. This Hubble sequence, often depicted as a tuning fork diagram, organized galaxies by their appearance and became a framework for thinking about galaxy types and evolution. For decades, astronomers debated whether the Hubble sequence represented an evolutionary track, with galaxies transforming from one type to another along the sequence, or simply a classification of different galaxy families that evolved separately. Modern understanding recognizes elements of both ideas. The Hubble sequence is partly an evolutionary sequence. Galaxies can and do transform from one type to another, but it's not a simple linear progression. Environmental effects, mergers, and internal processes can push galaxies in different directions along the sequence. Spiral galaxies that merge can become ellipticals. Disk galaxies that lose their gas become lenticulars. But ellipticals don't turn back into spirals because the violent relaxation processes that destroy disk structure are essentially irreversible. The discovery that well-formed spirals like Alakanda existed so early in cosmic history adds a new dimension to this picture. It suggests that the spiral branch of the Hubble sequence was populated very early, not gradually over billions of years. Understanding galaxy morphology at high redshifts is technically challenging. When we observe distant galaxies, we're seeing them at earlier times, but we're also seeing them in different wavelengths than we would observe nearby galaxies. Because of redshift, the visible light emitted by a distant galaxy is shifted into the infrared by the time it reaches us, while the ultraviolet light is shifted into the visible range. This means we're effectively observing different parts of the galaxy's spectrum. Ultraviolet light comes primarily from young, hot stars and regions of active star formation, while infrared light includes contributions from older, cooler stars and also from dust that absorbs starlight and re-emits it in the infrared. To properly understand the morphology of a high redshift galaxy, astronomers need to observe it in multiple wavelengths and carefully account for these effects. The James Webb Space Telescope excels at this because its multiple instruments can observe the same galaxy in different infrared bands, building up a complete picture. The images of Alakanda show remarkable detail for such a distant object. We can see the spiral arms, distinguish the brighter central region, and even identify some clumps within the galaxy that might be regions of enhanced star formation or stellar clusters. Each pixel in these images represents light that has traveled across most of the observable universe, carrying information about conditions in the early cosmos. The photons detected by Webb's instruments left Alakanda when the universe was young, traveled for billions of years through expanding space, passed through intervening clouds of gas and concentrations of dark matter that slightly bent their paths through gravitational lensing, avoided being absorbed by dust, and finally arrived at Webb's mirror where they were focused onto sensitive detectors and converted into electronic signals that were transmitted back to Earth and processed into the images that astronomers now study. It's an almost miraculous process when you think about it, and it's our only way of directly studying the ancient universe. Gravitational lensing, mentioned a moment ago, is actually an important tool for studying distant galaxies. When light passes near a massive object like a galaxy cluster, the gravity of that object bends space and time, causing the light to follow a curved path. From our perspective, this makes the background object appear distorted, magnified, or even multiply-imaged. Astronomers have learned to use this effect to their advantage. By observing distant galaxies that happen to be aligned behind massive galaxy clusters, they can study those distant galaxies in greater detail than would otherwise be possible, because the cluster acts as a natural cosmic telescope, magnifying the background galaxy. Some of the most distant and faintest galaxies known have been discovered and studied using gravitational lensing. In Alakanda's case, there's no indication that it's being gravitationally lensed, which means the images we see represent the galaxy's true appearance without magnification. This makes the level of detail visible even more impressive. The study of high-redshift galaxies is intimately connected with the study of cosmic reionization, mentioned earlier. During the epoch of reionization, which occurred roughly between 100 million and 1 billion years after the Big Bang, the neutral hydrogen gas that filled the universe was ionized by ultraviolet radiation from the first stars and galaxies. This was a crucial transition in cosmic history, fundamentally changing the state of matter in the universe. Understanding how reionization occurred requires identifying and characterizing the sources of ionizing radiation. Primarily young galaxies containing massive stars. The James Webb Space Telescope is discovering numerous galaxies from this epoch, allowing astronomers to measure their properties and estimate how much ionizing radiation they produced. Alakanda, forming sometime during or shortly after reionization, would have both been influenced by and contributed to this process. The radiation environment during reionization might have affected how gas could cool and collapse into galaxies, potentially influencing the rate and nature of galaxy formation. As we continue to discover more galaxies from the early universe, patterns are beginning to emerge. While Alakanda is exceptional in its clear spiral structure, it's not the only surprisingly massive or structured galaxy found at high redshift. Webb has revealed several galaxies that appear to have assembled large stellar masses earlier than models predicted. Some of these galaxies are extremely compact, with huge amounts of mass packed into very small volumes, unlike the more extended spirals and ellipticals we see in the nearby universe. Understanding the diversity of galaxy properties at high redshifts and how these early galaxies connect to the galaxy populations we see today is a major goal of modern extragalactic astronomy. One approach to understanding this connection involves abundance matching, a technique that links galaxies observed at different times to trace their evolution. The idea is to use the dark matter halo mass as a bridge between different epochs. Dark matter halos grow over time by accreting more dark matter and by merging with other halos. The growth history of dark matter halos can be predicted with good accuracy using simulations that follow only dark matter, which is computationally much simpler than simulating all the complex gas physics involved in galaxy formation. By measuring the properties of galaxies at different redshifts and matching them to the predicted dark matter halo populations at those times, astronomers can infer evolutionary connections. For example, a massive galaxy at high redshift likely resides in a halo that will grow into an even more massive halo by the present day, probably becoming the central galaxy of a galaxy group or cluster. This technique suggests that galaxies like Alakanda, despite being relatively young, are likely the progenitors of massive galaxies in today's universe, perhaps similar to the Milky Way or even larger. The concept of progenitors and descendants is fundamental to understanding galaxy evolution. Every galaxy we observe today has a history stretching back through cosmic time. It formed from smaller building blocks, grew through gas accretion and mergers, underwent periods of intense star formation and periods of quiescence, and perhaps experienced transformative events like major mergers or interactions with other galaxies. If we could watch a single galaxy's evolution like a time-lapse movie, we would see all these changes unfold. In practice, we can't do this because we only observe each galaxy at one moment in its history, but by observing many galaxies at different times and using theoretical models to connect them, we can reconstruct typical evolutionary histories. Alakanda gives us a snapshot of one moment in the life of a Milky Way-like galaxy when the universe was young, and by comparing it to similar galaxies at different ages, astronomers can trace how such galaxies evolve over billions of years. Star formation history is a key aspect of galaxy evolution that astronomers work hard to reconstruct. When did a galaxy form most of its stars? Was star formation continuous or bursty, concentrated in brief intense episodes? Has star formation continued to the present day, or did it cease at some point in the past? These questions can be addressed by analyzing the colors and spectra of galaxies, which encode information about stellar populations. Young stars are bright and blue, while old stars are fainter and red. A galaxy actively forming stars will have blue colors and show emission lines in its spectrum from ionized gas around hot young stars. A galaxy that stopped forming stars billions of years ago will have red colors and a spectrum dominated by absorption lines from cooler, older stars. By fitting models of stellar population synthesis to observed galaxy spectra, astronomers can infer the star formation history and age distribution of stars in the galaxy. For Alakanda specifically, preliminary analysis suggests that it has been forming stars for several 100 million years prior to the moment we observe it, building up its stellar mass gradually rather than in a single burst. This extended star formation history is consistent with the picture of a galaxy that has had time to settle into a stable rotating disk where gas is being converted into stars at a moderate, sustainable rate. If star formation had occurred in a single intense burst, we might expect to see a more compact, less organized structure, and the spectrum would be dominated by very young stars. Instead, Alakanda shows signs of multiple stellar generations, supporting the interpretation that it's a relatively mature system despite its youth in cosmic terms. The gas content of galaxies is another crucial factor in their evolution. Galaxies need gas to form stars, specifically cold molecular gas that can collapse under its own gravity to form dense clouds where star formation occurs. In the modern universe, spiral galaxies like the Milky Way contain substantial reservoirs of cold gas, primarily in the form of atomic and molecular hydrogen, distributed throughout their disks. This gas is constantly being converted into stars, but it's also being replenished by accretion from the intergalactic medium and recycled from stars through stellar winds and supernova explosions. The balance between gas consumption through star formation and gas replenishment through accretion and recycling determines how long a galaxy can continue forming stars. Elliptical galaxies, by contrast, generally contain very little cold gas and have low star formation rates, having either exhausted their gas supplies or lost them through various processes. In the early universe, gas was more abundant, and young galaxies like Alakanda would have had access to large reservoirs of primordial gas falling into their dark matter halos from the surrounding intergalactic medium. This abundant gas supply could support high star formation rates and also provided the material that settled into the rotating disk. As the universe aged and expanded, the density of intergalactic gas decreased, making it harder for galaxies to accrete fresh gas. Additionally, various feedback processes, from supernovae, stellar winds, and supermassive black holes, heated and expelled gas from galaxies, further reducing the available gas for star formation. These changes over cosmic time help explain why the star formation rate in the universe as a whole has declined dramatically since a peak around 10 billion years ago, an epoch sometimes called cosmic noon. By studying galaxies at different times, from the early universe through cosmic noon to the present day, astronomers can trace how the availability and behavior of gas has shaped galaxy evolution. Alakanda's disk structure implies that a substantial amount of gas settled into a rotating configuration early in the galaxy's history. The formation of a disk requires that infalling gas retains its angular momentum, the rotational motion it inherited from the initial distribution of matter in the universe. As gas falls into a dark matter halo, conservation of angular momentum causes it to spin faster, much like a figure skater spinning faster as they pull their arms inward. If the gas can cool efficiently, radiating away its thermal energy, it will settle into a flat rotating disk perpendicular to the angular momentum vector. The cooling process is crucial here. Hot gas has high pressure that resists gravitational collapse, but as gas cools, it loses pressure support and can collapse into a denser configuration. In the early universe, cooling could occur through several mechanisms, including radiation from excited hydrogen atoms and emission from trace amounts of heavier elements. The efficiency of gas cooling depends on the gas composition and density. Pure primordial gas composed only of hydrogen and helium cools less efficiently than gas enriched with heavy elements. Because heavy elements provide additional channels for radiating energy through various atomic transitions. This creates an interesting feedback loop in galaxy formation. The first generation of stars, formed from primordial gas, explode as supernovae and enrich the surrounding gas with heavy elements. This enriched gas can cool more efficiently, potentially accelerating the formation of subsequent generations of stars. If Alakanda benefited from early enrichment by an initial burst of star formation, it might have been able to assemble its disk more quickly than would be possible with purely primordial gas. Spectroscopic measurements of the heavy element abundance in Alakanda could help test this idea. The role of magnetic fields in galaxy formation and evolution is an area of ongoing research. Galaxies possess magnetic fields that permeate the interstellar medium, with strengths typically measured in microgauss, millions of times weaker than Earth's magnetic field but significant over cosmic scales. These magnetic fields can influence the behavior of ionized gas, affect the collapse of gas clouds during star formation, and play a role in driving galactic winds. The origin of galactic magnetic fields is not fully understood. They might be generated by dynamo processes, where the rotation and turbulence of electrically conducting gas amplifies weak seed magnetic fields into the organized fields we observe. Alternatively, weak magnetic fields might have been present in the early universe, inherited from even earlier cosmic epochs, and subsequently amplified in galaxies. Detecting and measuring magnetic fields in distant galaxies like Alakanda is extremely challenging with current technology, but future instruments might make this possible, adding another dimension to our understanding of how such galaxies formed and evolved. The chemical composition of Alakanda's stars provides clues about the conditions under which they formed. Different elements are produced by different types of stars and stellar processes. Oxygen, for example, is primarily produced in massive stars and ejected in core-collapse supernovae. Iron comes partly from massive stars but also from type Ia supernovae, which are thermonuclear explosions of white dwarf stars in binary systems. These different supernovae types have different timescales. Core-collapse supernovae explode shortly after massive stars form, within a few million years, while type Ia supernovae can occur long after star formation, typically after hundreds of millions to billions of years. By measuring the relative abundances of different elements in a galaxy, astronomers can constrain its star formation history and the types of supernovae that have enriched it. If Alakanda shows a high oxygen-to-iron ratio, it would suggest that the galaxy is young and has been enriched primarily by core-collapse supernovae from recent massive star formation, without significant contributions yet from the delayed type Ia supernovae. Dust in galaxies is another important component that affects both observations and physical processes. Dust consists of tiny solid particles, typically less than a micron in size, composed of elements like carbon, silicon, oxygen, and iron condensed into grains. Dust forms in the cool outer atmospheres of evolved stars and in supernova ejecta, and it subsequently dispersed into the interstellar medium. Although dust makes up only about 1% of the mass of interstellar material, it has outsized importance. Dust absorbs and scatters ultraviolet and visible light, obscuring our view of regions behind dusty clouds and causing distant galaxies to appear dimmer and redder than they actually are. Dust also re-emits the absorbed energy in the infrared, causing dusty galaxies to be bright infrared sources. This is one reason why infrared observations with telescopes like Webb are so powerful. They can see through dust to reveal hidden star formation and other processes. In young galaxies like Alakanda, the amount of dust present depends on how much heavy element enrichment has occurred and how efficiently those elements have condensed into dust grains. Early theoretical models predicted that dust would be rare in very young galaxies because insufficient time had passed for stars to synthesize and eject heavy elements and for those elements to form dust. However, observations with sensitive infrared telescopes have revealed that some high-redshift galaxies contain substantial amounts of dust, more than expected. This suggests either that dust forms more rapidly than models predicted, or that certain environments in the early universe were particularly efficient at producing dust. If Alakanda contains significant dust, it would indicate that chemical enrichment and dust formation occurred quickly in this system, further evidence of rapid evolution. The discovery of Alakanda represents more than just finding one remarkable galaxy. It symbolizes a fundamental shift in our understanding of how quickly the universe could organize itself after the Big Bang. Every new observation from the James Webb Space Telescope is rewriting the textbooks, forcing astronomers to reconsider assumptions that seemed solid for decades. The universe, it turns out, was far more capable and efficient at building complex structures than we ever imagined. When we look at Alakanda, we're not just seeing a distant collection of stars. We're witnessing a cosmic achievement, a galaxy that assembled itself with remarkable speed and precision in an era when the universe was still finding its form. The elegant spiral arms, the organized bar structure, the rotating disk of stars, all of these features speak to processes that worked with surprising efficiency in the dense, chaotic environment of the early cosmos. This galaxy managed to create order from chaos in less than 2 billion years, a timeline that challenges everything we thought we knew about galactic evolution. The broader implications of this discovery extend throughout cosmology and astrophysics. If galaxies like Alakanda could form so rapidly, what does this tell us about the nature of dark matter and its role in structure formation? What does it reveal about the physics of gas cooling and star formation in extreme environments? How do we need to revise our computer simulations to reproduce these observations? These questions are now driving research programs around the world as astronomers work to understand the full meaning of what Webb has revealed. Perhaps most importantly, Alakanda reminds us of the profound mystery that still surrounds galaxy formation. Despite decades of observations, sophisticated theoretical models, and powerful computer simulations, we're still discovering fundamental surprises about how galaxies come to be. The universe continues to exceed our expectations, showing us phenomena we didn't predict and couldn't have anticipated. This is the essence of scientific discovery, the recognition that nature is more complex, more interesting, and more wonderful than our theories suggest. As we continue to probe deeper into space and further back in time with instruments like the James Webb Space Telescope, we'll undoubtedly find more galaxies like Alakanda, each one teaching us something new about the early universe. We'll refine our models, update our simulations, and gradually build a more complete picture of cosmic history. But we should also remain humble, recognizing that the universe has been surprising us for as long as we've been looking at it, and it will likely continue to do so. The story of Alakanda is ultimately a story about human curiosity and ingenuity. It took decades of planning and billions of dollars to build the James Webb Space Telescope. It required the collaboration of thousands of scientists, engineers, and technicians across multiple countries. It demanded the development of new technologies, from advanced infrared detectors to deployable sun shields to precise mirror alignment systems. All of this effort was invested in a single goal: to see farther, to look deeper, and to understand better. And now, as the data flows back from Webb and reveals galaxies like Alakanda, we're reaping the rewards of that investment in the form of new knowledge about the cosmos. Looking ahead, future telescopes and observatories will build on Webb's discoveries. Ground-based telescopes with enormous mirrors, the extremely large telescope, the giant Magellan telescope, and the 30-meter telescope, will provide complementary observations with even higher resolution in some wavelengths. Future space missions might include telescopes specifically designed to study the formation of the first galaxies or to map the three-dimensional distribution of matter in the early universe. Each new instrument will add pieces to the puzzle, helping us understand how galaxies like Alakanda fit into the broader picture of cosmic evolution. The discovery of this ancient spiral galaxy 12 billion light-years away also connects us to the universe in a profound way. The atoms in our bodies, the carbon, nitrogen, oxygen, and heavier elements that make up our cells and molecules, were forged in stars that lived and died billions of years ago. Some of those stars might have existed in galaxies like Alakanda, creating the elements that would eventually find their way into later generations of stars, into planets, and ultimately into living beings like ourselves. When we study distant galaxies, we're not just looking at alien structures far removed from our existence. We're studying our own cosmic heritage, tracing the chain of events that led from the Big Bang to the present day, from primordial hydrogen to complex life. Alakanda stands as a testament to the universe's capacity for creating beauty and structure. Its spiral arms sweep gracefully through space, shaped by gravity and rotation, illuminated by billions of stars. Though we'll never visit this galaxy, though it exists so far away that the light we see left it before our solar system even formed, it captures our imagination and drives our desire to understand. In that sense, Alakanda is not just a scientific discovery but an inspiration, a reminder of how much there is to explore and how much we have yet to learn about the cosmos we inhabit. As observations continue and our understanding deepens, Alakanda will take its place in the history of astronomy alongside other landmark discoveries that transformed our view of the universe. It joins the ranks of the first quasars, the cosmic microwave background radiation, the accelerating expansion of the universe, and countless other findings that have reshaped human knowledge. Each discovery opens new questions even as it answers old ones, propelling science forward into unexplored territory. And so the journey continues, from one cosmic mystery to the next, driven by wonder and guided by the light of distant galaxies reaching across the universe to tell us their stories. Claude is AI and can make mistakes. Please double-check responses.